It's my pleasure to announce today's speaker, and this is Horst Wallrabe. Horst Wallrabe has a 35 years business career in the pharmaceutical industry. Then he joined University of Virginia, Department of Biology in 1997 as a full-time community scholar. Developed expertise in molecular cell biology, FRET and FLIM microscopy, resulting in more than 20 peer-reviewed papers based on own and cooperative research. The title of his talk is Tales from the FLIM Crypt, Optimizing Imaging, Fitting and Analysis of Auto-fluorescent, NADH, NADPH and FAD to measure cellular redox states in live cancer cells. So now I hand over to Horst. Horst, please start.
All right. Thank you, Hauke. Well, first of all, thank you for inviting me to give this talk. And before I go on, I just want to acknowledge the people that are on the title page, namely Rufan Kao, Shagufta Alam, Rehman Alam, Carsten Siller, and of course, Amasik Feryasamy. Rufan is the research scientist in the Keck Center. Shagufta also involved more on the biology side. Carsten Siller did some heavy lifting to develop the software and help us with several software solutions. And of course, Dr. Amasi Feryasamy, who is the director and founder of the Keck Center, who I met, I guess at the end of the 90s, when he was just building his FLIM instrument. Before that, there were a couple of other research scientists that have gone to other places now. One is Zenek Sevindrish, who's somewhere in northern New England doing his magic, and Yuan Cheng Song, who's working with ISS. So all of these people helped me a great deal to get to the point I am now. When I first started on the FLIM side with FLIM FRET and other things some 10 years ago. My first slide is just to give a quick state of the union on FLIM, which is not directly only linked to FAD and NADH, which is, let me check. Here we go. The kind of preamble of the lifetime estimation methods, which is quite important. Very recently, in fact, in the JBO July 2020, the Melissa Scala group published a very nice review, which explains the different methods of curve fitting with about 300 different references, the phasor plot, deconvolution methods, and all of these actually can be found in the Becker Hickl handbook. And but nevertheless, it's nicely summarized here, and it's worth looking at. The interesting part, really, which of course has been heard before, is the machine learning and artificial intelligence approaches that are happening all over the place now, including autonomous cars, et cetera, et cetera. It's almost in all areas of science they are introduced, and I would not be surprised if this is going to go mainstream, in the next 5 or 10 years, if it's not already quite there. Each of these methods, in fact, in that review, have shown to be specific advantages and disadvantages. And, therefore, the bottom line, as in most biomedical experimentation that we're involved in, is we need to establish the most appropriate FLIM method based on advantages and disadvantages and see, where we get. Obviously, the most important pillar in all of experimentation is to have positive and negative controls, to state the obvious, and then we can compare it with biomedical assays and biochemical assays and other microscopy approaches. What I'm going to talk about in my presentation is based almost exclusively on the Becker Hickl imaging and analysis software, because that's what we have in our center, and this is what we use on a regular basis. All right, so like 10, 11, 12 years ago, those are the kind of questions that I had where I got all this help from the people I mentioned initially, to work my way through it. because there are many parameters and the combinations matter for some optimal light fitting process. That's the model. So what do we use? Multi-exponential or incomplete. It does make a difference. The instrument response function, auto or measured. Components, we have three choices. How do we establish them? The threshold, what do we do about them? Scatter and offset, we have two choices, either to fix them or let them float. Chi-square, the goodness of fit. How do we balance that to get the correct number? The shift, absolutely, there's a lot of what is the word, agreement on how that should be done, but when do you fix it? And then batching is a very convenient and time-saving method, but is it always correct? Well, I can tell you, no, it's not always correct, and you need to get back to fit the one or other image that is not quite processed in
some interruption, Horst. I think there was.
Okay. All right. We'll see. Share screen. Do I have to go back, or what's the deal?
I think it is since 1 minute.
Let me go back to the.
So it happened on slide 3.
Okay, I have to share again, yeah?
Yeah. So no, yeah. Now it is already shared. You have to.
All right.
To start the presentation again.
Okay. Well, we'll go back to where we stopped. All right.
Yes.
So.
Can you start the presentation, please, again?
From the beginning?
No. Just press the start button on PowerPoint.
Okay. Yeah. Yeah. Sorry. I understand what you're saying. Where's my cursor, damn it? My cursor, my pointer doesn't go to the bottom.
Aye.
Okay, here we go. All right. So as I said, all of these answers can be found in the handbook, details I talked about. And so some of my presentation will explore these questions, and how the different parameter combinations actually will change the answer. So here are some of the things I have already got quick answers for. Incomplete, offset, and scatter are the main variables that I will comment on. The components are mostly known. I talked about the IRF. The threshold is easily established by putting the cursor on a non-cellular area and just check the trace and see where in that on the Y scale, on the logarithmic Y scale, where in fact the trace starts, and just change from the default of 5 to maybe 50 or whatever that background is. The bin-in option is a bit of a balancing act. The first priority is to have enough photons for correct fitting, and the rule of thumb would be if you have a one component, it should be around 100 on the logarithmic scale, and for two components it should be more than 100, maybe closer to 1,000. Although to be honest, with NADH, I hardly ever reach the 1000 with the 60-second acquisition time that we are using, and it's not needed. So, you know, the lifetimes and the chi-square bin is increased, and you can check actually whether, in fact, your chi-square actually changes a great deal. All right, the scatter with hybrid detectors and no ambient light source and no second harmonic, I think should be always fixed to 0. The offset in the incomplete should also be fixed to 0, and multi-exponential should be let float. Chi-square and shift, other than letting binning and components getting them right, randomly place your cursor on the cellular areas with shift floating, and then fix shift at the level where the chi-square falls between 0 and 7. And if during the batch fitting, you actually have an image which has very bad chi-square, it's almost invariably that the shift needs to be changed. And all the other conditions remain the same. You simply go back, change the shift until the chi-square becomes acceptable, and then that particular image is processed or fitted with the right shift level. Batch fitting, I already talked about a little earlier. All right, here are the main variables. Again, I covered most of them already in red box. You have your components up here. You have your, in this case, 2 components. You have your 2 lifetimes and 2 amplitudes. And here's your shift, which was fixed after we acquired an acceptable chi-square. You have your 2 scatter and offset set. Now this is a incomplete model. Here's my threshold again. If this here finds that the trace of the cell areas gets you to a higher level than 5, then you just check it. The bin, we have variably used bin 1 and then bin 2 for NADH. My chi-square is acceptable. Here's my IRF and the top of my trace, and here are my residuals with a scale of -5 to +5, and they very nicely go basically at the 0. So all it looks good here, and you know, the next one is that you really need to test with a FLIM standard. We're using ATTO425, and we have compared it with Hela cells. So here is ATTO425 at multi-exponential model. The offset is flowed and the scatter is fixed. That is the standard multi-exponential recommended parameter setting. However, by floating the offset, the leftover pulse is incorrectly seen as noise. And that is something that will alter the lifetime calculation. And therefore, TM is incorrectly shown at 3 nanoseconds, because we know that the correct average lifetime is 3.6 seconds for this particular standard. So in the incomplete model, we have the offset and scatter fixed to 0. The leftover pulse is of the unfinished decay is really interpreted correctly and is included in the fitting process, and therefore we do get the right lifetime expected for ATTO425. And you know, we apply the same thing to the Hela cells, and we're getting with a multi lower TM, and the incomplete, we believe, correctly interprets the TM. All right, so we talked about the RF. As I said, we measure it regularly with our urea crystals and second harmonic. And we find, as it is shown here, that regularly what they call synthetic or automatic SPC image RF delivers the same results. And so we are mostly just using this function in SPC image. The phasor plot is a very good on-the-fly assessment. For example, in this case, of drug response. Vladislav, a couple of webinars ago, gave a lot of details, so I won't belabor it right now here. But on that line across on the right-hand side of that semicircle, you have the lower unbound lifetime of 0.4 nanoseconds, and on the left side, the 3.9 nanoseconds, the bound lifetime, and the line across is your average amplitude weighted lifetime. And since we always see an increase of that TM and a 2%, which is driving the TM, you can see that you have a lower in the control and the expected much higher level in the cancer-treated Hela cell. So the only thing I can say, we do not use it as a endpoint analysis because it does not replace our particular discrete quantitative ROI-based analysis, which, as I will show in more detail, actually goes to single cell segmentation and describing the cytosolic glycolysis and the mitochondrial oxphos in separate times. So just to describe very briefly how we are set up and how we do this, as I said, Hela cells, we are treating them on stage. We use identical fields of view. We start with the control, then comes the treatment. In this case here, I will just show the 60-minute results, with a couple of exceptions, but that's really the critical time when we see the maximum change. We have a size 780 NLO system that's coupled with a 3-channel SPC 150 Becker Hickl lifetime board. We have 3 hybrid detectors, temperature control, stage, humidified blood gas. We use multi-photon 740 for NADPH and 890 for FAD, and we switch them sequentially. And the emission is for NADH is 460 to 500, and for FAD 520 to 560. We find that this way avoids any kind of back bleed through into the NADH channel by FAD, or vice versa, any bleed through from NADH into the FAD channel. And imaging conditions, total darkness. We have the microscope and the detectors enclosed in a blackout box. We use two-component incomplete model offset scalar fixed, and the shift optimized for a good chi-square. And these things I'm probably going to repeat a few times as I go through my presentation. Our Keck Center for Cellular Imaging developed this FLIR assay, which is a alternative to the intensity-based ratio, which has certain advantages, avoiding any kind of intensity-based artifacts, particularly useful for tissue sections. And it is a ratio of NADPH, a 2%, which is the bound version, and FAD, a 1%, which is the bound or quenched FAD section. And this has been applied to several cancer lines, other non-cancer lines. We have used it in neurons and also published in the EMBO journal last year. And it's based on single cell segmentation. We have 2 pixel regions of interest, RIs, analysis by each single cell. And we are therefore can interpret and explore inter and intra cell heterogeneities. And we can also, by this method, separate the mitochondria from the cytosolic signals. And then, as I mentioned earlier, we have several macros and codes and plugins to analyze these large data sets. And we end up with some 30 FLIM parameters, including the main ones that you're very familiar with, the ratios. And we're also trying to interpret the NADH and NADPH ratio. As you see, we have 5 publications that spell out in great detail what is going in there. Now, one of the most important things that we needed to establish right at the beginning is actually that our NADH signal, which is the photon signal, actually matches the mitochondria, because otherwise all the assay angles that we are using and we've described, are questionable. So here's the mitotracker in red FM, in B, and on A is the NADH signal. Then we merge the two, and we can actually say we've published that the correlation between the two is in excess of 90%. So there's a very good correlation. This is important because, we have 60 seconds acquisition, and we know that there are kinetics involved in mitochondria. But we are also saying that there is, during that imaging time, during that acquisition time, they may change their morphology with scission and fission. But there's unlikely in 60 seconds to be any biogenesis. So we're still dealing with the same pool of mitochondria in that short acquisition time. So anyway, that's the basis of our assay, and we are pretty confident that the NADH signals, the higher NADH signals, where more of the NADH is concentrated, is a pretty good estimation of where the mitochondria are. So the different analysis steps are, well, the first ones because those are the regular, let me just get my thing out of the way. Okay, is the fitting process and then the export. From that, we establish a stack of photon stack. This we normalize because, as I will show a little later, over time courses, we do see a drop in photons. And since we want to pick up the morphology, which is still visible, but at a lower photon count, we are using this normalization step, which works most of the time. Not all the time, but which works most of the time. With that, we get a little bit of the background, but since we segment the cells, these are not picked up in our RY selection, which is shown here. So here we are, first of all, segmenting the cells. We also incidentally zero the nucleus in either thresholding or by hand at the moment. We are actually working on integrating this whole thing into one software. And so here you see the field of view ROIs, in fact, for the mitochondria. These guys here, which also show some kind of signal, will actually not be picked up because we are restricting all the ROIs only that are inside the segmented cells. The next step then is that we split cyto and mito simply by thresholding. We're taking the lower threshold of the mitochondria with a couple of gray levels below as the upper threshold of the cytosolic signal, which is always lower, and the background becomes, above the background becomes the lower threshold for the cytosolic. And then, we do our magic in the quantitative analysis by using Python and Excel. And all of that, what I just explained, is really in those words below here. All right, so one of the questions that's always come up is, can we use fixed specimens? Is there any utility on using fixed material? And here again, we're using NADH and FAD as our trial run, because that's what my talk is about. The photons clearly, well, let me first explain. So here we have the live Hela cells. We image at first at control. We take 5 fields of view. We wash them on microscopy stage. We add formaldehyde, fix them for 5 minutes. We wash them again, PBS is added, and then the same 5 fields of view are re-imaged, and then we do the standard quantitative analysis, which I just described. Now, the photons clearly in NADH go down. Surprisingly, they go up. I don't know why. But anyway, that's what we found. The amplitudes are somewhat affected, and there's some overlap, but they're affected. Whereas the lifetimes in both cases are virtually untouched. So if you just go for lifetimes, at least on this example, and I'm showing some literature examples in a minute, the lifetimes themselves are actually not changing during fixing. But we do not routinely use fixed specimens. But we have applied it to FLIM histology slides, particularly with prostate cancer pathology department, and so it does work. I mean, you do get FLIM signals. The photon counts are affected, amplitudes a little bit. I mentioned that already, and the overlapping standard deviation show the lifetimes are really not affected. And there are two examples in the literature that I just briefly mentioned, which these are labeled samples. They were formalin fixed. These are ovarian cancer tissue sections, and they said that they had little impact on FDA lifetimes. And the next reference, and I'm sure there's others, is formalin fixation and paraffin embedding, and these are also histology slides. And again, they did not find any change in the lifetime. So for certain applications, it might be of interest to use some fixed samples. We are not using them very often. Okay. All right. So is bleaching an issue? Well, that's an interesting question, because I don't really know when the photon count goes down, as it did in this one. I haven't shown it. Whether it is biology or whether it is, i.e., is there a change in abundance in fluorescently abundant protein, or is it truly bleaching? Anyway, the answer is T1, T2, A1% amplitude show little change. There's a little change, but again with overlapping standard deviation. So we don't really see any bleaching, except that the photon count does go down. And I'm giving some more details in the next slide. So this was done with 30 seconds acquisition up to 300 seconds, but each at their own, these were done separately, each at their own wavelength, not the switching that we do normally, which I'll show in a minute. So photons drop with overlapping SD, lifetimes are unchanged, amplitudes, there's some change. So here's that one where we do the same thing as we just did, except now we're doing what we normally do in our imaging. We first image 60 seconds at 740 for NADH, and then follow up with another 60 seconds for 890. So, and this is done at 5 time points for this particular exercise. And the total exposure time, therefore, for NADH, is the only one I'm showing, is 9.5 minutes. That's a long time. And here are the results. So here's the photon count, clearly goes up from control over these 4 stages to 60 minutes. And the distribution in the histogram shows it again. Here's T1. Well, virtually no change. Here's T2. Again, no change, even after 9.5 minutes. Here's the amplitude A1 fraction. There's some change. I don't know whether we call it dramatic or not. And here's A2, and this is obviously the opposite, since two of them are 100%. And here's TM, which is influenced by all of these 2 lifetimes and the 2 amplitudes, the average amplitude. So the result is, basically, we've checked this out. Now we can basically cut out the intermediate time points. We can just take the control image, going ahead, going forward, and cut out the intermediate points, and simply go wait for 60 minutes, and then we don't have those shifts even in the photon count. Okay, so that deals with the bleaching side. So let's just briefly go back to the general cellular energy metabolism for which we are using NADH and FND as a metric. Glucose, not that I want to talk a lot about biology, is degraded by pyruvate upon reduction of NAD plus to NADH in the cytoplasm. That's the glycolysis. The oxidative phosphorylation is the main source of energy in eukaryotic cells. It's happening in the mitochondria. This involves, again, NADH and FAD. When we use the one-photon intensity-based redox ratio that was pioneered by Britton Chance, it's usually based on the whole cell area to study cell metabolism. Here, intensity is used basically to approximate molecular abundance and its change of that abundance. And it has served a very good, what am I doing? Has served a very useful purpose, and it's still being used. The disturbed cellular metabolism, and in particular mitochondrial dysfunction, occurs in many, many different pathologies. It's even closely related to aging also. So the redox states serve as a very useful metric to see those changes in pathologies as wide as cancer cells all the way to Alzheimer. So here we are, just some very brief data presented for the Hela cells treated with doxorubicin, where we are applying FLIR, our FLIM-based redox ratio for the whole cell, and compare it with mito and cyto, i.e. with oxphos and glycolysis. And again, here just the control of a 2% as a metric, and here we see it after 60 minutes. So here is probably already, that we have established in another paper published by Shagufta as a first author, where already at 60 minutes we can predict apoptosis setting in. So these three bars are comparing the whole cell, which is the open, there you go, my pointer wasn't working. So here's the open bar is in fact the whole cell. The black bar is the cytosolic, and the somewhat gray bar is the mitochondrial oxphos. So you can see it over this time scale that oxphos here is really the larger of the two, and you can see here the FLIR for the FLIR ratio, and then the two components of FLIR, and you can see that's really the 82% that is mainly driving the FLIR ratio, at least in this case. I can't say that it is in every case, but this is what it is. So FLIR increases after doxorubicin, and the FLIR changes are mainly driven by the bound NADH. And here is a quick correlation between FLIR, to make my point, and NADH 82%. And our publication, Cytometry A, kind of comments a little more on this, how three different ways of analyzing your FLIM data are really quite useful, and you have the option of doing it, several ways to establish the metric. So here's almost 100% correlation. All right, so here we have 49, almost 50 single cells, and we have somewhat arbitrarily split them into three categories. I mean, not arbitrarily, we just used certain ranges measured by the percent change from the control, median change from the control to the 60 minutes treatment. And the difference really is that using the mitochondrial, the red one, and the blue one is cytosol, and the change up to 60 minutes is this little open bar, yeah? And you can see, first of all, the heterogeneity that you find even in each category. And the response to drug is highest here in category 3 and lowest in category 1. And here you see the distribution on the right in those histograms. And you see that the actual endpoint of the particular mitochondrial oxphos is not that dissimilar. The difference is really where your control starting point is, i.e. those with a lower metabolic rate, those cells, reach after treatment similar, not exactly the same, but very similar points of their increase. So what's happening, as I mentioned a little earlier, is in cancer cells upon, very often upon treatment, the cancer cell is trying to stay with glycolysis, suppressing oxphos for two reasons. The main reason is in ROS defense and to avoid the apoptosis starting point. However, by the treatment working, the oxphos normalizes or goes back to a more correct energy production process, and therefore you see that the 2% oxphos is going up. All right, so before I go into 10 minutes more in comparing some different applications of fitting models, just a quick summary on what we've seen so far. The TSV imaging protocol and fitting process can be a little challenging for new users, but issues of acquisition, time versus power, time acquisition that is, multi-exponential versus incomplete and other variables are manageable. I've found this out over time with some help consulting the book, the Becker book. You'll get through to an optimized assay that works over time and for repeated applications to your particular scientific objectives. The photon loss, bleaching, and the time course does not appear to affect lifetimes in these auto-fluorescent molecules. They will, because it depends on your acquisition time. They will affect labeled molecules. So there you are having to have this balancing act between laser power and acquisition time. And usually the rule of thumb is, lower your laser power and rather increase your acquisition time as a better balance. FLIM and fixed specimens produce variable results. It's the background, but basically lifetime seems to be unaffected by it. Our novel-based redox ratio FLIR certainly offers an alternative to the current intensity-based one. It's particularly important for light scattering tissue specimens where really the intensity method is not suitable. And our quantitative assay does separate mitochondria from cytosolic signals quite reliably by using discrete region of interest selection, and then combine it also with single cell analysis. So let me get to the rest of my presentation. So the question is, what happens to FLIM results when we change the model and or other fitting parameters? Well, each slide, earlier slides showed, in fact, the difference in lifetime by fitting multi versus incomplete model. And I'll just briefly put that up again when we use the FLIM standard for ATTO425. There's general agreement, when the at what stage the shift should be fixed. But what about offset and scatter? Those are two variables I have mentioned earlier. And as I said, my lament is that publications rarely describe their full fitting protocol. And so here I'm going to show you some examples of the results of different fitting parameters and their combinations. All right, so here are the four the first one with the first two with the slightly colored background are the ones that we are suggesting are appropriate. The first one is I for incomplete multi-exponential with the offset and the scatter fixed to 0. That says here, the shift across all of these is the same thing. We optimize it after we've seen chi-square you know, within acceptable ranges as we are putting our cursor over the morphology of our field of view. The next one is multi-exponential. I mentioned this is used for very short lifetimes. This is multi-exponential with the offset letting float and the scatter being put to 0. And then I just put in a couple of other variables, with the last one actually is, that's how I started. Because this is what the Becker Hickl SPC image software was. You know, it was multi-exponential was the default, and the scatter and offset and shift are floating because, you know, at that time they're not yet fixed. I didn't know any better. Now that's, you know, over a decade ago, with the help of the people I mentioned. I think I got it right in the meantime, pretty soon after that. But that's what, you know, beginners that come into our tech center very often assume that's what default is, and that's what we should do. Anyway, so by applying these different fitting conditions to the same data, it will demonstrate, you know, how it will influence the different FLIM parameters. The two are the really two ones that we're supporting, and the ATTO425 I'll just briefly put up on the screen in a minute again, and the Hela cells are at control in 60 minutes, and you know, all the things I've said before, they're evaluated at 2 by 2 pixel ROI data. And we have about 5,000 data points that are at the bottom of the numbers that I'm going to show. So that's to repeat it ad nauseum. We consider incomplete, offset and scatter fixed to 0 as mostly the correct choice. Multi-exponential with the offset to float and scatter fixed is the second choice for short lifetimes. All right, so here's again the repeated, the 425, the multi-exponential with the offset floating gives the wrong answer with 3 nanoseconds for the TM. And when we use the incomplete model, where the leftover pulse is correctly interpreted as unfinished decay of the previous pulse and is included in the fitting process, shows the correct 3.6 nanosecond, which is the known lifetime. All right, so here are the chi-squares, both for FAD and for NADH. And, you know, if you just judge these different combinations of fitting procedures by the chi-square, you can say, well, all of them are really delivering acceptable chi-squares. They're under 2 and they're, you know, floating around 1. So that's not your way you can actually judge them. So the solid red is our preferred incomplete. The mottled red is the multi-exponential, which is the second choice. And those are just combination with the blue mottled, and here are the, you know, the conditions. And with the blue mottled is the one that, you know, is basically default before you make any changes to the software. And so as I mentioned earlier, even when I do batch control and I do find batch processing, and if I do find that the chi-square in 1 or 2 FLIM images does result, rarely does, but does result actually in bad fit, then the software will tell me that, and all the eliminations are logged. You know, if it's on 1%, maybe 0.3%, 0.5%, I don't bother. They're not going to change the statistics. If it's more, I'll go back and refit the particular image that is affected by it. So let's now go to the T1, T2, TM and investigate the same data and processed or fitted by different conditions. So here's T1. Well, here's the average, and here is the histogram of the control over time. So you do get, you know, if you use that blue, the solid blue, which, you know, is probably the least of the recommended ones, it will give you a very different, well, very different. Instead of 400 picoseconds, it'll get you to over 500 picoseconds. If you at 60, it has already made some difference in the output after treatment. So clearly, that model is not recommended. This one here, the solid red, is the one that we recommend, the incomplete with scatter and offset fixed. And the blue line is the one we do not recommend under any circumstances. And the mottled red is your multi-exponential with the offset to float and scatter 0. All right, but you can see the differences there can occur. And that is really, that story really continues when you go to the T2. Now, the T2 is somewhat interesting because here's our preferred, and here's the multi-exponential, also the second choice. And there's quite the difference between the two. And this may or may not be to do with the NADPH, but I'm guessing. I don't have any proof of that. But you are seeing already in the longer lifetime that you will get very different lifetimes in the control, and that is continuing after the treatment with doxorubicin. And here's the TM, which of course is influenced not only by those two lifetimes here, but also by the amplitudes, A1 and A2. So again, without beating it to death, you can see there are clear differences as to what kind of model you choose. Now, FAD will show you very similar responses to the different fitting conditions, and particularly the longer lifetimes seem to be more affected than the shorter lifetimes, where you see less of a difference. The key one that really I stumbled on this was actually the, I'm ahead of myself. This is the next. So this is FLIR. Let's just discuss briefly FLIR. FLIR and the two amplitudes. So with FLIR, it follows, I mean, since we are using the amplitudes below here as the ratio between a 2% and a 1%, i.e. these two here, which produces the actual FLIR, we see clear differences in what combination of fitting parameters you are going to use. So again, I don't know that if you are going to do some kind of control, and I don't know how you put the FLIR control on other than looking at this control, there has to be some other control to find out which actually is the correct way for doing it. I think the ATTO425 is probably the most reliable, or other FRET standards, the most reliable indicator on which model is the most obvious, except for certain situations where, you know, again, the Becker Hickl handbook offers a lot of examples where one or the other might be a better option. For us, for this NADH, the first incomplete offset and scatter to 0 is, we believe, the right approach. That's the one I was about to come to, which is actually this very seminal paper by the Becker group, which, and that group is really well experienced, has published some excellent scientific work. But in this particular paper, I could not find the fitting conditions, because I tried it then with the incomplete model that we normally use, and it didn't quite work. And if you're looking at here at splitting this by that formula at the incomplete model, in the control, you get an NADPH share of the two between NADH and NAD of 60%, and for the NADH, 40%. If you are using the multi-exponential, you get a 30% and a 70%, a huge difference. So clearly, that formula here works only with a particular, and they've done a lot of work, and I don't wish to denigrate at all the work that they published in Nature Communication, because that is very, very well supported. But the actual repeating it is extremely difficult if you don't know the exact fitting conditions they used. And maybe their data could be reconfigured with, the formula could be reconfigured with the, if Becker is listening, reconfigured with the existing data points and apply the incomplete approach and see whether there is a formula somewhere which will still do the same trick and get the right answers that they have provided by doing a lot of those biochemical assays to support their findings, which are very important because it's, we're looking for an imaging solution, how to split these two signals that cannot normally discriminated by their fluorescent properties. So I'll come to my final summary. FLIM clearly has enriched the field of light microscopy in the life sciences, and it will clearly make further contributions, particularly in clinical applications. It does already with eye examinations, and I am sure that the what do you call it, IR intelligence and the machine learning will make its way into the FLIM world. There are certain complexities in research, etc., which I have mentioned because we don't know exactly how some of the FLIM assays were executed. There needs to be a concerted effort by authors, editors, referees to insist that in publication all fittings and analysis parameters are detailed. I think this is for the goodness of the FLIM field, so we can repeat exactly experimentation that otherwise, we don't know how they did it. The processes are somewhat complex, the 900 pages of the Becker book, very impressive Becker book, testifies it, but, I think it's manageable, and the reduction of these complexities are achievable, even though we know there are always some exceptions, and for this you have these other options to employ. So with proper controls, and again, everybody knows that, and periodic tests, FLIM standards, measuring the instrument response function, signal for noise, number of photons, etc., users will eventually establish and hopefully declare their best practices for their instrument setup and their scientific aims, and let us share, their experiences. Thank you very much.